Well, hello everyone. Thank you very much for being here. My name is Damien DeRoche. I'm the Executive Brand Manager of Consumer Electronics Test and Development, and I will be your host for this afternoon's webinar. As I'm sure most of you know, Consumer Electronics Test and Development magazine is the world's foremost magazine that looks at all the latest test, inspection, and certification solutions for consumer electronic devices. I'd like to offer a warm welcome to everyone who is in attendance here at this webinar today, which is presented by Dan Pino, who is the Senior Director of RF Engineering at the company Element Materials Technology. As I'm sure you're aware, is one of the world's leading global providers of testing, inspection, and certification services for a diverse range of products, materials, and technologies. Dan Pino is a highly accomplished RF engineer with extensive experience in wireless technologies and regulatory compliance. Dan has a proven track record of leading teams to develop comprehensive test plans and ensure products meet FCC and Canadian regulatory standards. His expertise extends to EMC, EMI, and RF radio testing, making him a valuable asset in navigating the complex landscape of wireless technology development and compliance. With over a decade of experience as a TCB, FCB technical reviewer, he is a trusted authority in regulatory compliance and client advocacy. And Dan has worked with Element since 2005 and has served in his current role as Director of RF Engineering since 2017. I'm very shortly going to hand you over directly to Dan. Thank you again very much for being here. Do also be aware that after this presentation, at the end, there will be the opportunity to ask questions in a Q&A session. I'm sure those of you who are attending will have questions today, and if so, please do add them to the Q&A box, and we'll endeavour to answer these at the end. The subject matter for our webinar today is the evolving landscape of satellite communications. And without further ado, I will hand you over to Dan. Thank you.
All right. Thank you so much, Damien, for that introduction. I really appreciate it. And I would also like to extend my welcome and thank you to everyone who registered for this webinar. I am Dan Pino, Director of RF Engineering with Element Materials Technologies Connected Technologies Business Unit, based out of the East Coast, USA. And I'd like to take some time today to discuss the topic, as Damien mentioned, of the evolution of satellite communications. So for the material I plan to cover today, I plan to go through the following topics, starting with a brief introduction to satellite communications, which I'll be saying that a lot throughout the presentation. So that's more colloquially known as SATCOM. So after that, I'll discuss how SATCOM works, just to try to lay down the foundation for that. Go back and to the early years to see how satellite communications has evolved over the years, then discuss the current state and emerging trends in SATCOM. I'd like to briefly as well touch on some of the regulatory requirements and some of the work done in the regulatory space, and then discuss also some of the challenges faced by some of the SATCOM users today, and try to round things off with the future outlook, which in my opinion is very bright. So I definitely plan to touch on some of that. So without further ado, a brief introduction to SATCOM. What is SATCOM at its base? I think a quick definition is in order. SATCOM is essentially the use of space-based satellites to transmit and receive signals for use in data, voice, and video communications from satellites to Earth-based stations. This technology obviously would enable connectivity to remote locations, and more importantly, it plays a pivotal role in navigation systems such as GPS and GNSS. So you can see that by using satellites, we would be able to establish long-distance reliable communications without having to rely on the classic terrestrial infrastructure like base stations that are commonly in use today. And so a brief introduction as far as how SATCOM works. So SATCOM, for the purpose of this presentation, and really for a lot of the ongoing work going forward in this field, generally falls into three flavors, and each of these different types of satellites are kind of distinguished by the orbital altitude of the satellites from the Earth. The closest being low Earth orbit, or LEO, which is located within the 160 to 2,000 kilometers above the Earth. Medium Earth orbit, or MEO, is about 5,000 to 20,000 kilometers above the Earth. And geostationary orbit is about 36,000 kilometers above the Earth. These numbers are roughly, give or take, a few thousand kilometers. I think different entities would classify them at different distances, but these will roughly cover the correct distances for these operation of these satellites. So LEO and MEO satellites, for example, are kind of closer to the Earth. So if you were to look up in the sky, you could see that they would actually be kind of moving relative to you, the user on the Earth, just because it rotates at a different speed of that of the Earth. Given their close proximity to the Earth, you could see that, yeah, I think you can see my marker there. Since it's so close to the Earth, you can kind of tell that one satellite in, for example, LEO orbit would have a very small cone of radiation, so you would need multiple of them to provide more global coverage to the entirety of the Earth. Some of the common uses for a LEO satellite is for example, used for communications, as we'll see throughout this presentation. A very common use for like a MEO satellite is the global navigation type satellites that are in use today, like GPS. For a geosatellite, that is one that is specifically located above the Earth's equator, and it travels at the same speed as the Earth. So if you, the observer on the Earth, were to look up at a geosatellite, it would appear just like a unmoving star up in the sky because it's spinning at the same speed that you are essentially on the Earth. One common use, or a couple common uses for geosatellites, are for weather prediction models, and also for satellite radio and TV. So next slide. One thing that I do think is kind of important to point out, because I've seen two terms that are very similar, kind of used almost analogously, but I would like to point out that there is a very subtle difference between the two terms of geosynchronous and geostationary with regards to those two orbits around the Earth. So the main similarities is that both geosynchronous and geostationary satellites orbit the Earth at approximately the same altitude of 36,000 kilometers. The main difference is that a geosynchronous orbit, while it does have the same rotation period of the Earth and of a geostationary orbit, which is about the 24-hour period, the main difference is that the geosynchronous orbit is not necessarily around the equator of the Earth, and as such, you can actually notice that it kind of travels in almost like a figure eight pattern above your head, whereas the geostationary, as I mentioned, is, as the term implies, stationary in the sky. So as you can tell in this picture on the right, for example, you can tell that like a geosynchronous orbit tends to have, it can have like some kind of inclination with respect to the Earth's equator. And so yeah, I do think it is very important to distinguish those two, because I myself in the past have also used them analogously, even though that might not be the case. So for the purpose of this presentation, the satellites that we will discuss are mainly of the geostationary variety. So here's a pretty helpful table, I think, as far as outlining the various differences kind of side by side of the main orbital altitudes of the different types of satellites that are in orbit today, with the main three that we discussed being the GEO, MEO, and LEO satellites. So for the GEO satellite, since it's up at 36,000 kilometers, you can kind of infer that it does have very superior coverage, right? Very large coverage of the Earth with less satellites required, maybe 1 to 3 to kind of cover the entirety of a large sector of the Earth. One of the main disadvantages is that because it is so high up, and because RF waves are like everything, obviously limited to the speed of light, the latency as far as getting a signal from the Earth up to this satellite then back down to Earth is very high, in the 250 to 280 millisecond range. While this doesn't seem too bad on the surface, this would be very poor as far as if you were trying to do like a real-time conversation with somebody. You're out on like the battlefield, or you need to get a message out to someone quickly. This is not the typical satellite you would use for this type of communication. Some of the actual advantages of it, though, are, as I mentioned, that there are fewer satellites required in order to provide a much larger coverage to the Earth. It does have that fixed location above the Earth, and it tends to have a longer lifespan of 10 to 15 years. Some of the disadvantages, kind of as I mentioned, is since it is so high up in the Earth, it does tend to suffer a significant amount of RF path loss due to large distance, which means that the satellite inherently is going to require more power and a much higher antenna gain to overcome that path loss. And it does have that high latency that I mentioned previously. For a medium Earth orbit satellite, the latency obviously goes down a significant amount due to the fact that it's orbiting much closer to the Earth. It still has a relatively large coverage since it is higher above the Earth, but it does, in essence, require more satellites to provide that same coverage, on the order of maybe 5 to 10, depending on the different geographies. These type of satellites also tend to have a pretty long lifespan, as far as 10 to 15 years, similar to a GEO satellite. Some of the disadvantages are that the cost of satellite launches in general are relatively high, on the orders of millions, as you guys might have seen in some of the more recent satellite launches. The propagation loss is still relatively high because it is still a pretty long distance to cover, up to the 20,000 kilometer range above the Earth. The last one that we would discuss today is the LEO orbit. One of the main benefits of it is the fact that it does have this extremely low latency because it is so close to the Earth. So this is something that's much more ideal for like a real-time communication. If you want to make a phone call, if you're based in the US, you want to call somebody in the UK, for example, something like a LEO satellite would be much more amenable to that, just because of the low latency. One of the drawbacks is that in order to provide that worldwide coverage, you would need to have lots more satellites to provide that kind of coverage. And that's all kind of covered here. And as there are a lot more satellites in low Earth orbit, that means that the space up there is getting a bit cluttered, just because of so many launches that have gone on in the past, and some of the ones that are going on now, and the ones that are forthcoming. As such, the average lifespan of a LEO satellite tends to only be about 5 years, due to it being cluttered, and due to also the fact that there's a lot of atmospheric drag happening at such low altitude. If you think about a low Earth orbit satellite orbiting the Earth, since it's so close to the Earth, it constantly has that battle of having to fight against the Earth's gravity. So it needs to use its engines, obviously, to keep it within that stable orbit, but at the same time dealing with the Earth's gravity and other atmospheric components. Okay, so now I look back at some of the early and formative years of satellite communications. So as you all have, I'm sure undoubtedly seen, there's been multiple hundreds of satellite launches over the years, each accomplishing very different things, right? So rather than spending a whole presentation talking about every single one, I've decided to just try to identify some of the more earlier launches that have kind of been the catalyst for some of the later technologies and some of the more recent advancements in satellite communications. So if we take it all the way back to 1945, a gentleman by the name of Arthur C. Clarke was the first to conceptualize the idea of a geostationary orbit. In his early on diagram, he essentially sketched out the Earth, and his vision was to have 3 satellites providing full coverage of the Earth, traveling, as I mentioned, in geostationary orbit, because I guess in some circles, Dr. Clarke was was almost like a founding member of this concept. Sometimes the geo orbit is referred to as a Clarke orbit as well. So it wasn't until about 1957 when we saw the launch of the first satellite, being the Sputnik 1, launched by the USSR into low Earth orbit. Very early on kind of design, kind of like a ball with like 4 different legs for the antennas. It was the first human-made satellite launch into space, usually mainly used for the purpose of monitoring and to show, hey, you know, as the world, we can actually do this. This is actually within our reach. And so unofficially, the launch of Sputnik, as you all remember back from your history lessons, this triggered the unofficial beginning of the space race between the USSR and the United States. So fast forward to 1958, as when the US launched its signal communications by orbiting relay equipment, or SCORE for short, which would be its unofficial entry into the space race. And this was thought of as the world's first communication satellite, and it was the first time that we were able to get a voice broadcast from space. I believe, if I remember correctly, that there was a Christmas song played to the president from this satellite. So fast forward to 1962, this is when NASA launches a Telstar 1 satellite into low Earth orbit. So this would become the very first satellite to allow for transatlantic communications. This is going back to the example I mentioned. If you want to communicate using a satellite between, for example, the US and the UK, this would have been one of the first satellites to accomplish that. Fast forwarding a little bit, 1964 saw the launch of the SYNCOM-3 satellite, which would become the first satellite launched into true geostationary orbit. Now I mentioned true geostationary orbit because there was a prior SYNCOM-2 mission. The SYNCOM-2 satellite did actually reach geostationary altitude of the 36,000 kilometers above the Earth. However, it was more of a geosynchronous orbit because it did have an incline to the equator. So technically, as you know, shown in a previous slide, it was not a true geostationary. That's what the SYNCOM-3 was for. This was a truly revolutionary launch because it was the first satellite capable of transmitting a live TV signal. It was used to transmit live coverage of the 1964 Summer Olympics to over 1/3 of the globe. In the same year, 1964, Intelsat was established, which is the International Telecommunications Satellite Organization. And it was essentially the first true international consortium of nations with the singular goal of developing satellite constellations for the advancements of global communications. Over the next few years, several satellite missions of the Molniya satellites would go up from the USSR. They would be used to establish a proprietary satellite communications network within the Soviet Union. The following year, in 1966, the ATS-1 satellite was launched, and this was the first satellite to provide continuous weather data and communications. So that would lead to the rise of future satellites, which are in use today, obviously, to predict weather over various regions in the world. In 1972, the Landsat-1 satellite was launched, and this was the first satellite designed specifically for environmental monitoring. It was the first satellite designed to truly study the topography and geography of planet Earth. In 1978, saw the GPS Block 1 satellite go up. So this was the first true satellite constellation used for GPS purposes. 1990 is a very famous one, as I'm sure you all know, is the launch of the Hubble Space Telescope. This was a revolutionary satellite launch in the sense that it was the first satellite to provide truly high-resolution images of the space and our solar system. It continues to be in use today, and it is still one of the really great high-resolution satellites in orbit today. In 1997, the Iridium-1 satellite constellation was launched into low Earth orbit, and it was used to essentially provide, rather to establish the Iridium constellation, which is still used for global satellite phone coverage today. So as mentioned, in the subsequent years, there would go on to be multiple other satellites launched over the years, which would essentially build on some of those more earlier satellite designs, which were really truly the first ones to establish some of the things that we know and use today. Excuse me. So as far as covering some of the current state and emerging trends in satellite communications, as mentioned, several satellite launches over the years have greatly contributed to various fields like communications, navigation, Earth observation, and space exploration. Several LEO satellites have gone up into orbit, especially more recently, to provide narrowband communications. That's a great thing to have. The limiting factor there is that a narrowband communication is really kind of meant for like a short messaging system, right? So you're not going to be able to transmit high definition audio or like high-res video over those narrowband links. We've seen a growing number of satellite constellations go up into low Earth orbit by companies like SpaceX, which has put up their Starlink constellation. Other satellite manufacturers like OneWeb and Amazon are also continuing to build out their network of satellites to provide critical services such as broadband internet, television, and communications. SATCOM is also more commonly started to be used for the expansion of 5G networks to provide coverage, especially to remote areas where there may not be proper terrestrial base station coverage. And it's also SATCOM has also been used to support a vast network of IoT devices in more recent applications. We've also seen over the years geostationary satellites from companies like DirecTV and SiriusXM that have been used to provide services like internet, satellite coverage, television, and other broadband broadcasting applications that we know and use fairly commonly today. SATCOM is also being used to play a pivotal role for disaster recovery and emergency communications. Just think of the unfortunate a situation that happened most recently in the U.S. with the hurricane that we had that tore up the southeastern part of the U.S. There's still millions down there without power currently, but with the assistance of satellites, some of these families without communications to their terrestrial base stations have been able to use some of the emergency satellites to get communications back out to their loved ones. Another application is that the government and military has also been using SATCOM with that being geostationary orbit satellites in particular for secure and encrypted communications, surveillance and reconnaissance as well. You can tell how that would be critical for a government faction, especially in the age of cybersecurity. And one kind of last use of modern day use of satellites is what you may have heard of as CubeSats. So a lot of time these CubeSats are deployed in large numbers, like hundreds or thousands of these. The CubeSat itself might be as small as something like a shoebox. So obviously the efficiency, the use of just one CubeSat is very limited. But when you throw a lot of these up in like as part of a large constellation, you can use them for applications such as imaging and other scientific research. So now, as far as covering some of the regulatory updates and some of the work done by some of the regulators with a focus on the FCC, since that's the majority of what we've seen a lot of lately, especially in the US. With all the advancements in satellite communications, it's becomes essentially very clear that the regulators also share in a large portion of the responsibility for managing the spectrum and the usage of these satellites and their services. In fact, in May 2024, the FCC adopted and released its report and order and a notice of proposed rulemaking, the document called FC 24-28, in which it lays out the framework for something it calls supplemental coverage from space, or SCS for short. So as you can kind of infer by the name, this is essentially achieving that goal of what if you are somebody on a mountain bike on the mountainside and you accidentally slip off and fall and you can't get a message out to like a first responder, to a loved one, and there's no base station coverage in your area. The goal here is that you would be able to leverage the data from the satellite in space to provide supplemental coverage to your already existing land-based coverage. So the SCS effort establishes a means and a framework by which the satellite vendors can leverage their existing satellite systems in orbit to provide expanded cellular coverage from space to Earth-based stations such as a tablet or a handset like all of us have today. So it's important to note that the FCC governs the spectrum usage in the US regardless of whether the RF comes from a terrestrial base station, from a mobile network operator, or from a space station. So just because you're operating and providing coverage from space from a satellite, that doesn't mean that you are exempt from the FCC's rules. So two of the main ways that we've seen satellite coverage from space are by companies that kind of fall into two different large categories. There are the companies such as Iridium, Globalstar, EchoStar, Skylo, etc., that are using their own proprietary L-band and S-band spectrum. So that's companies using spectrum, dedicated spectrum by the FCC under their Rule Part 25 in the 1.6 or 2.4 gigahertz spectrum to provide satellite coverage from space. And then the newer flavor, which is the newer flavor of satellite coverage, which is due to this latest FCC NPRM, is leveraging the existing spectrum owned by mobile network operators that are land-based, such as Verizon, T-Mobile, AT&T. These mobile network operators obviously own the licenses to the bands that we know and use every day, such as Band 2, Band 13, Band 4, and so on and so forth. So several devices on the market today actually already have regulatory approval to use satellite communications. I think one of the first big examples was when the iPhone 15 came out a year or so ago. It was touting the use of the emergency messaging services. So this would be perfect for the case discussed previously, where, for example, you're on a mountainside and you fall off and you don't have terrestrial coverage to get a phone call out, like a 911 phone call out for help for a distress signal, but you can leverage the existing satellite coverage for that. as kind of alluded to earlier, a key component of this NPRM established by the FCC is that any satellite vendor attempting to offer SCS services must have an agreement with a terrestrial MNO. And so the reason for that is, as mentioned previously, someone like Verizon, very well known, they own Band 13, they have the license for that. The license is granted to them by the FCC. So a satellite company can't just come in and use Band 13, right? They have to have an agreement in place, and the NPRM actually states that out specifically. As mentioned here in the bullet point, that any satellite vendor offering SCS must have a prior agreement in place with the mobile network operator. So this has inherently led to the rise of several partnerships between existing mobile network operators and several players in the satellite space already. Some of the more common ones, just to list a few, are, for example, AST Space Mobile, which actually back on September 12th was successful in launching its first 5 satellites, which they call it the Bluebirds, which was used or is going to be used over the years to establish a true framework for LTE coverage from space. So AST Space Mobile, as we speak, has a partnership, a standing partnership with Verizon and AT&T. We've seen SpaceX with their Starlink constellation of satellites show or have an agreement with T-Mobile, and Eutelsat, or now known as OneWeb, also has a partnership with AT&T to use their spectrum to provide coverage from space. Some other things to note on the regulatory side, there is dedicated spectrum all over the FCC spectrum allocation table. So currently the use of the 17 gigahertz spectrum is commonly used for GEO applications, but there is a new NPRM that came out, I believe, a couple months ago or so, that is seeking comment from the public as far as using that same 17 gigahertz spectrum for non-GEO fixed satellite services. So for the purpose of this conversation, non-GEO refers to some of the other low Earth and lower Earth and medium Earth orbit satellites that we've discussed in the past. So this this RNO seeks to establish the technical rules, likely under Part 25, that would enable effective and, more importantly, compliant usage of non-GEO satellites, while also taking into account the other key aspect is that by using these satellites in lower and medium Earth orbit, you want to ensure that those satellites to come are not causing any interference to the incumbent GEO satellite users that have been there for years, for decades. As mentioned, the FCC is currently soliciting feedbacks and comments and feedback from the community on this proposal. And as with other RNOs and NPRMs, they will take a look at those comments and spend a few months using that to kind of shape any future regulations on this usage. So with all those advancements in satellite communications over the years, it's also very important to look at the other side of the coin, which is some of the challenges that SATCOM faces today, of which there are several, unfortunately. One of the large ones is space traffic and debris. So with the growing number of satellites going up, especially into low Earth orbit, this causes, as you can imagine, a lot of congestion in space. And a lot of these satellites that have been up in low Earth orbit for years, or that were launched over the past 30, 40 years, have now kind of become derelict satellites that are no longer tended to, and they eventually kind of come down and crash and burn through Earth's atmosphere. But that also causes a lot of debris in the wake, right? So that debris obviously causes congestion as far as getting up new satellites, but it also only stands to increase the RF attenuation from other satellites that are up in higher orbit. As mentioned, the use of more satellites in space also leads to spectrum congestion. If I have one low Earth orbit satellite operating next to another one, then how do you ensure that those two satellites don't interfere with one another, or that they can work in a collaborative fashion so as not to cause interference issues? As mentioned previously, also a geosystem largely known for its large latency issues. So that introduces a very difficult challenge as far as using it for a real-time application. There are still high costs associated with rocket launches in the multi-millions of dollars just to get a launch window, and then to hope that your satellite gets up into space. And if it doesn't, then you're back to square one as far as redesigning and scheduling another launch, which obviously pushes back your timeline. And then there's also the issue of dealing with regulations and licensing. As mentioned, the FCC is the entity responsible for the regulations, working along with NTIA for the licensing within the US. But at the same time, there is physically only so much space in orbit to launch up a satellite, right? So these spaces known as slots are very highly coveted, almost like oceanfront property, right? It's very hard to get your name into that slot to be able to launch a satellite. And so you constantly have fighting between several SATCOM operators looking to obtain licenses and paying millions or billions of dollars in what has now become a very highly competitive market. Of course, there exist several bandwidth and throughput limitations, largely stemming from the fact that there's so many other satellites in orbit from with which you are competing, and also just the reality that some of these long distances lead to a lot of RF propagation losses, which essentially would degrade signals and obviously lead to a limitation on the throughput. Power and efficiency issues are kind of running rampant as well. With something like a geosatellite, for example, as I mentioned previously, it's so high up off the Earth at roughly 36,000 kilometers that it requires a significant amount of power and very large gain or multiple large gain antennas just to be able to provide adequate coverage to Earth. There's also the also ongoing issue of what the space weather conditions are. Something as seemingly insignificant like a solar flare, cosmic rays, geomagnetic storms. These can easily disrupt satellites, throw them off orbit, maybe work to reorient the antenna in a way that significantly reduces the throughput or the efficiency of these satellites. And then there's obviously the atmospheric conditions with the Earth changing, obviously with global warming. There's different, as an example, there's different issues to deal with signals passing through the Earth's atmosphere. There's obviously a lot more attenuation involved when you throw in rain, snow, or even on a very cloudy day. That obviously serves to decrease the throughput of that satellite link. And then lastly, it's worth mentioning that there's also strategic and geopolitical concerns. Obviously, every nation is kind of responsible for their own airspace. And for example, one nation, kind of as we saw early on in the early 50s or the mid 50s when we saw the space race, a launch by a satellite, a launch of a satellite by the USSR is obviously seen, perhaps as a threat to the rest of the world. Like, oh, okay, these guys launched a satellite. So what does that mean? Are they spying on us? Well, now we have to put our name in the hat as well to make sure that we can keep up with that technology and those advancements. Excuse me. So despite all of the challenges and most recent advancements that have been discussed so far, I do believe that there is a very bright future as far as the future evolution of satellite communications, stemming all the way back from the first conceptualization of the geostationary orbit back in 1945. Several applications and several satellites have gone up since then to revolutionize the way that we use SATCOM in general. So if anything, SATCOM, I think, is even more exciting in the coming years than it was in the early formative years. So several new concepts and scientific advancement, scientific advancements have been used to advance satellite communications, as I'll kind of mention in the upcoming slides. One of them I thought was extremely interesting is the research going into quantum communications, whose primary purpose would be to leverage the principles of quantum mechanics to enable highly secure and ultra-fast communications. This is extremely interesting in the sense that data transfer, as we know today, is mainly done by digital ones and zeros, which are obviously, as you guys have seen from some of like the cybersecurity risks and some of the hacks we've seen over the recent years. Quantum communications would use quantum bits or qubits, which has a significant advantage over the classic digital ones and zeros in the sense that it increases the reliability of the encryption as far as making it nearly unbreakable. The concept of using a quantum key distribution, for example, is a good illustration of this. In this QKD scenario, this is where, for example, two parties are looking to establish communications, and one of them would generate a quantum key that is proprietary to the two communicating parties. So any attempts to hack or to disturb that communication essentially causes a shift in the quantum state of the photons used for that communication. And that shift in the quantum state is actually a lot more easily detectable than it would be to try to detect a hack of a classic binary 1 or 0 communication. So this would, as you can see from this, significantly improve the security and the reliability of a communication. The first such quantum satellite actually went into orbit by China back in 2016. It was the Mesius satellite, I believe it's called. And back in 2021, NASA proposed itself the framework for what would be an eventual quantum network infrastructure program, which is continuing to develop and being researched today. Something else that it's very close to everyone here, everyone's fairly aware of artificial intelligence and all the advancements that our artificial intelligence has brought forth to engineering in general. So there are also ongoing developments to use and leverage the power of AI to supplement both terrestrial and satellite-based networks. In particular, AI can be used as to generate like a smart algorithm of sort to help to model behavior and movement patterns off satellites. Something like this, you can see, can be very powerful to try to mitigate, for example, like the collision between two satellites, or in order to dodge some of the spatial debris that some of the satellite vendors are dealing with today. As mentioned, AI is being increasingly used to model and used to help predict usage patterns by the various users. So for example, it can detect, just as an example, that, hey, between the areas of 4 to 7 p.m. within this specific region, I'm going to need a lot more resources routed to this area to help out with that. So by teaching an AI algorithm to use that, you can essentially put the management of the network, of those network resources on autopilot to ultimately enhance the reliability and the performance of that network. So AI can be used to manage the operation of large satellite constellations, especially like the CubeSats that mentioned previously, that have hundreds of thousands of satellites in orbit that would be very difficult to kind of manage by hand. Well, you can kind of train those all as one constellation and manage your resources accordingly by teaching a potential AI algorithm for predictive maintenance as well. AI can be used, for example, to determine, hey, this one particular sector of your CubeSat constellation is starting to significantly degrade. So I can predict that in 2-3 years, it's going to need to be replaced or brought down back into back to the Earth for like a repair. One of the other areas where I think we've seen probably the most headway being made is in the satellite to device or direct to device communications, which is what I mentioned earlier, where you have a satellite communicating directly to a land-based device, most importantly, like a phone or a tablet. So you've got companies like SpaceX with their Starlink constellation, others like Iridium, and Globalstar, which again has that partnership with Apple to provide the emergency SOS texting messages. Other companies like AST Space Mobile, working, all these companies working to provide supplemental coverage from space from their already existing satellites or satellites that are soon to go up into orbit to supply satellite coverage to user handsets on Earth. As mentioned previously, back in September, AST Space Mobile launched their first 5 commercial satellites, which they've called Bluebirds, into low Earth orbit. Some of the preliminary pre-launch data that they've been able to provide to the public on the capability of these Bluebirds is such that they would be able to provide broadband download speeds of somewhere in the range of kind of like a low to mid-level Earth-based 4G speed. This is truly remarkable, as far as taking a huge step from what was previously a narrow band signal for just texting messages to being able to leverage, even accomplishing a low-end 4G speed from space is, is a truly remarkable advancement for humanity. So there's also the widespread use of proprietary spectrum from some other companies, as I mentioned previously, like the Iridiums and the Globalstars, using their own proprietary spectrum to continue to not only use their existing proprietary spectrum, but some of the challenges with that is that using the proprietary 1.6 and 2.4 gig spectrum, well, then that means that in order to provide coverage to like a cell phone, well, that cell phone has to have the complementary chipset to be able to communicate within that. And it's not really easy, especially for like the phone device manufacturers, to install these chipsets by the thousands, by the millions, as they're selling these iPhones and Galaxy devices. So I think the next big move for a lot of these companies that have previously been using the proprietary spectrum is to expand their service offerings by allowing their satellites to provide coverage in the more widespread 3GPP bands, which is used on a global basis. And those are the bands that we all know and use on the daily, like the bands 2, 4, 5, 12, and so on. the use of the 3GPP spectrum by these satellites essentially means that just about all modern day handsets within, we'll call it 3 to 4 years, are essentially already available and capable of communicating directly to a satellite, and it's essentially waiting for the satellite to turn on the service. So that brings us to the end of our presentation. I'd like to thank you again for your time and listening in on this. Here's our contact information, as Damien mentioned earlier. I would certainly love to hear from you. If you've got any questions, I can take them either now, or you can feel free to reach out to us, myself personally, at this email, or our generic Elements contact email. And also just a brief blurb that with the upcoming Mobile World Congress in Las Vegas in the USA coming up next week, I guess next Tuesday, specifically through Thursday, Element will have a booth 1006. So if you happen to be in the area, we will have some reps running that booth, and we would certainly love the opportunity to speak with you about this or any other topics that may be burning in your mind. So with that being said, Damien, I'll turn it back over to you, and thank you guys so much for listening in. Damien, I think you're muted still.
Sorry, I've just realised that, so apologies. Amazing. Many thanks, Dan, for that highly informative presentation. I'm sure everyone will agree, very insightful guidance on SATCOM, its variation and wide range of uses, how it works, emerging trends, that sort of thing. Yeah, as Dan mentioned, I think without further ado, we'll launch straight into any questions we may have. I do have one here. If anyone else has any additional questions, please do pop it in the Q&A box. But we'll start with the following. Dan, with all of the advancements in satellite communications, what kind of testing services are required, and does Element support that testing?
Right. Yeah, that's a great question. Thank you so much for that. Right. So as I mentioned earlier on the regulatory update slide, especially on the FCC side of things within the U.S., there are ongoing efforts, obviously, to lay out the framework for updating some of the rules that are governing the uses of that spectrum from satellites. So in a nutshell, Elements is very closely tied with those updates from the FCC. We've got a lot of good contacts at the FCC and are working also with several of the satellite manufacturers to be able to provide perhaps one of two services. Certainly from the regulatory perspective, just generic testing under FCC's Part 25. And also, if you're a satellite vendor that happens to have your own proprietary product certification plan, we're certainly able to kind of work with you on that to test certain things like the reliability, the throughput, power, bandwidth, so on and so forth.
Great stuff. Thank you for that. Unless we have any further questions, obviously, as Dan's already pointed out, he can be contacted on the email address shown on the screen. But Dan, thank you so much for that presentation today. Before we draw a close to the proceedings, please also note that this webinar will be available online on the Consumer Electronics Test and Development website. Once again, thank you very much to Dan, and thank you to everyone joining us here on the CETD webinar platform. And I wish you all a very pleasant evening or morning or night or wherever you may be.
Thank you all so much. Take care.